Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to settle in wherever you are. Let your body sink into comfort, releasing whatever tensions the day has left behind. There's nowhere you need to be, nothing you need to accomplish, just gentle exploration ahead. Where in the world are you right now? A quiet room where you can finally let your mind rest. A peaceful space where the day's noise has faded. Wherever you are, you're exactly where you need to be. Tonight we're going to explore something that didn't happen but easily could have. We'll discover what would have occurred if 3I/ATLAS, that mysterious interstellar visitor from 2024, had taken a slightly different path through our solar system. What if its trajectory had brought it not past the sun at a safe distance, but dangerously close to our star? We'll understand the physics of extreme solar approaches, see how comets behave when they venture too near the sun's surface, and contemplate the spectacular destruction that occurs when ice meets stellar fire. But don't worry, this isn't going to be a journey through violent chaos or terrifying scenarios. Instead, we'll move slowly and thoughtfully through the physics and beauty of what happens when fragile visitors from the cosmic cold encounter the most powerful object in our solar system. By the end, I think you'll find not fear, but appreciation for the delicate balance that allows comets to survive their passages and the spectacular processes that occur when that balance fails. If you enjoy these calm explorations of cosmic what-ifs and celestial mechanics, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this community of curious minds, so settle in now. Let your shoulders drop, releasing tension you didn't know you were carrying. Take a slow, deep breath in, feeling your lungs expand and release it gently. Feel yourself sinking deeper into comfort with each exhale, and let's begin our slow drift through the scenario of 3I/ATLAS, approaching too close to the sun, exploring what physics tells us would happen when interstellar ice meets stellar fire. There's nowhere you need to be, no conclusions you must reach. Just listen, and let the exploration unfold like the patient work of gravity pulling a comet toward its fate. Let's begin by understanding what actually happened with 3I/ATLAS during its passage through our solar system in 2024, because appreciating what could have occurred requires first knowing what did occur. 3I/ATLAS was discovered in January of 2024 by the Asteroid Terrestrial Impact Last Alert System, ATLAS for short, operated by the University of Hawaii. The discovery came from automated surveys scanning the sky for moving objects. When astronomers calculated its orbit from the initial observations, they immediately recognized something special. The trajectory was hyperbolic, meaning the object was moving fast enough to escape the sun's gravity. It wasn't bound to our solar system. It was an interstellar visitor, only the third such object confirmed at that time. The orbital calculations showed that 3I/ATLAS would make its closest approach to the sun, called perihelion, in late May of 2024. The predicted perihelion distance was approximately 0.39 astronomical units from the sun's centre. An astronomical unit, AU, is the average distance from Earth to the sun, about 150 million kilometres. So 0.39 AU meant 3I/ATLAS would come within about 58 million kilometres of the sun at its closest point. To put this in perspective, that's inside Mercury's orbit. Mercury, the innermost planet, orbits at an average distance of 0.39 astronomical units, though its eccentric orbit takes it as close as 0.31 astronomical units, and as far as 0.47 astronomical units from the sun. 3I/ATLAS would pass through the inner solar system at roughly Mercury's distance, experiencing solar radiation and temperatures comparable to what Mercury experiences, though only briefly as it whipped past on its hyperbolic trajectory. This was close by solar system standards, close enough that the comet experienced significant heating and developed an active coma and tail. but it wasn't dangerously close. The Sun's visible surface, the photosphere, is at about 0.005 astronomical units from the centre, roughly 700,000 kilometres radius. 3I/Atlas would pass more than 50 million kilometres from the Sun's surface. That sounds like a lot, and it is. At that distance, the comet was safe from the most extreme solar effects. It would heat up, sublimate ice rapidly, possibly fragment from thermal stress, but it wouldn't be destroyed by direct interaction with the Sun itself. The trajectory brought 3I/ATLAS through the inner solar system at a steep angle to the ecliptic, the plane where most planets orbit. It approached from the southern solar hemisphere, passed through perihelion, and departed toward the northern hemisphere. The hyperbolic excess velocity, the speed it would have relative to the Sun once far away, was calculated at roughly 34 kilometers per second. This high velocity confirmed its interstellar origin. No object orbiting the Sun would have that much excess energy. The timeline of the passage was relatively quick. From first becoming easily observable in January to fading beyond detection in August, the entire observational window was about 7 months. The peak activity occurred around perihelion in late May. During that peak, 3I/Atlas was sublimating ice rapidly. Water vapour, carbon monoxide, carbon dioxide, and other volatiles were streaming off the nucleus, creating a coma hundreds of thousands of kilometres across. The solar wind and radiation pressure pushed material into a tail extending millions of kilometres behind the comet. But the nucleus itself, estimated at roughly 3 kilometres across initially, survived perihelion intact, at least as far as observations could determine. If it fragmented, the pieces remained close enough together that telescopes couldn't resolve them as separate objects. This survival was expected. Comets regularly pass perihelion at distances similar to or closer than 3I/Atlas's 0.39 AU. Most survive, though they may lose significant mass and undergo structural changes. The actual trajectory was thus interesting, but not extreme by cometary standards. 3I/Atlas was a typical sun-grazing comet in terms of its perihelion distance, experiencing substantial heating but not approaching the truly extreme conditions that occur much closer to the Sun. But trajectories aren't fixed by the universe. They're determined by initial conditions, by where an object starts and how fast it's moving when it enters a gravitational system. Small changes in those initial conditions, an interstellar comet entering the solar system from a slightly different direction, or with slightly different velocity, can produce dramatically different trajectories. If 3I/Atlas had been travelling just a few kilometres per second slower, or if its direction had been angled differently by just a few degrees, its perihelion distance could have been much smaller. Instead of 0.39 astronomical units, it might have been 0.1 astronomical unit, or 0.05 astronomical units, or even closer. Interstellar objects arrive with random trajectories determined by their path through the galaxy and the chance gravitational influences they experience during their journey. There's no reason the trajectory had to be what it was. It could have been different, and if it had been different, if 3I/Atlas had approached much closer to the Sun, the physics of that encounter would have been dramatically different from what actually occurred. The comet might not have survived. It would have experienced conditions found almost nowhere else in the solar system. Understanding what would happen in such a scenario requires examining the physics of close solar approaches, the extreme environment near the Sun, and how cometary materials behave under conditions far more intense than what 3I/ATLAS actually experienced. That's the journey we're about to take, exploring the hypothetical but entirely possible scenario where 3I/Atlas's trajectory brought it not past the Sun at a safe distance, but into the extreme environment very close to our star's surface. The actual passage was spectacular. A close passage would have been apocalyptic, at least for the comet. Let's explore what that apocalypse would have looked like step by step, as physics and stellar power overwhelmed a fragile visitor from interstellar space. To understand what would happen to 3I/Atlas in a close solar approach, we first need to understand the environment near the Sun, the extreme conditions that exist in that region of space. The Sun is a massive sphere of plasma, gas so hot that electrons are stripped from atoms. Its mass is about 330,000 times Earth's mass, accounting for 99.86% of all mass in the solar system. The energy source driving the Sun is nuclear fusion in its core, where temperatures reach 15 million degrees Celsius. At those temperatures and pressures, hydrogen atoms fuse into helium, releasing tremendous energy in the form of photons and neutrinos. That energy radiates outward through the Sun's interior over hundreds of thousands of years, eventually reaching the surface. The visible surface, the photosphere, has a temperature of about 5,500 degrees Celsius, far cooler than the core but still unimaginably hot by any terrestrial standard. Above the photosphere lies the chromosphere, a thin layer where temperature actually increases with altitude, reaching about 20,000 degrees. Above that is the corona. The Sun's outer atmosphere, where temperatures mysteriously jump to over 1 million degrees despite being farther from the heat source. This temperature inversion, cooler surface and hotter corona, is still not fully understood. Magnetic fields and wave heating are thought to be responsible, but the exact mechanisms remain active research topics. At 0.01 astronomical unit, 1% of Earth's distance, about 1.5 million kilometers from the Sun's center, the intensity would be 13.6 million watts per square meter, 10,000 times Earth's solar constant. And if somehow you could get to the Sun's surface, 0.005 astronomical units, the radiative flux from the photosphere itself would be about 60 million watts per square meter. These numbers are staggering. To put them in perspective, standing on Earth in direct sunlight, you feel about 1,000 watts per square meter. That's enough to cause sunburn after extended exposure. Now imagine 10,000 times that intensity, or 100,000 times, or 1,000,000 times. Materials exposed to such intense radiation don't just heat up. They vaporize almost instantly. Metals melt. Rock turns to vapor. Ice doesn't even have time to melt. It's sublimating directly from solid to gas, and then dissociates into individual atoms from the sheer energy input. The magnetic field near the Sun is equally extreme. The Sun's global magnetic field is weak, similar to Earth's field strength. But localized magnetic structures like sunspots and active regions can have fields thousands of times stronger. These magnetic fields shape the corona, create loops and prominences extending hundreds of thousands of kilometers above the surface, and accelerate particles to high energies. When magnetic field lines reconnect, they can release energy equivalent to billions of nuclear bombs in solar flares. Coronal mass ejections, CMEs, hurl billions of tons of plasma into space at speeds up to several thousand kilometers per second. If a comet happened to be near the Sun during a CME, it would be engulfed by an expanding cloud of million-degree plasma travelling at extraordinary speeds. The solar wind near the Sun is also much denser and faster than at Earth's distance. Close to the Sun, the wind has particle densities of millions per cubic centimetre, compared to about 5 particles per cubic centimetre at Earth's distance. The gravitational field near the Sun is proportionally stronger as well. At Earth's distance, solar gravity produces an acceleration of about 0.006 meters per second squared. At 0.1 astronomical unit, that acceleration is 100 times stronger, 0.6 meters per second squared, comparable to surface gravity on the Moon. At the Sun's surface, solar gravity is about 274 meters per second squared, 28 times Earth's surface gravity. This immense gravitational pull would exert tidal forces on any nearby object, potentially tearing it apart if it came too close. The Roche limit for a comet approaching the Sun would be around 2 to 3 solar radii, depending on the comet's density and structural strength. Inside that distance, tidal forces from the sun's gravity would overcome the comet's self-gravity, causing structural disruption. All of these environmental factors, extreme radiation, intense magnetic fields, powerful gravity, energetic plasma, combine to create an environment near the sun that is utterly hostile to any solid object. Very few natural objects venture into this region and survive. Those that do are mostly sun-grazing comets from the Kreutz family and related groups. These comets pass within a few solar radii of the sun's surface, experiencing extreme conditions, but sometimes surviving due to their trajectories that minimize time in the most intense environment. 3I/Atlas, in our hypothetical scenario, would be entering this environment. How it behaved, how long it survived, what happened to its structure and composition would all depend on exactly how close it came and how fast it was moving when it reached perihelion. The actual environment it would experience would be more extreme than anything measured by spacecraft, more intense than conditions on any planetary surface in our solar system, more hostile than anywhere outside a star's interior or a supernova explosion. Understanding this environment sets the stage for understanding what would happen to a 3-kilometre ball of ice and rock falling into it. The environment wouldn't just heat the comet. It would attack it from every direction with radiation, particles and forces that would systematically disassemble it. As 3I/Atlas approached the sun on a closer trajectory than it actually took, the first effects would be increased heating long before it reached perihelion. Even at Earth's distance, 1 astronomical unit, the comet would have been warming. Ice near its surface would begin sublimating, though slowly. The solar flux at 1 astronomical unit is sufficient to maintain water ice sublimation, which is why comets typically become active somewhere between 2 and 3 astronomical units from the sun. 3I/Atlas actually became active around 2.5 astronomical units. When observers first detected a coma forming, this is normal behaviour for comets containing water ice. The sublimation temperature of water ice in vacuum at 1 AU distance corresponds to the solar heating at that distance. But in our hypothetical closer approach, the heating would accelerate dramatically as the comet crossed inside 1 astronomical unit. At 0.5 astronomical units, halfway to the sun from Earth's orbit, the solar intensity would be 4 times Earth's level. The surface temperature of the nucleus would rise. Ice that was stably frozen at greater distances would begin sublimating vigorously. Water ice would stream off as vapour. More volatile ices, carbon dioxide and carbon monoxide that sublimate at even lower temperatures, would have been lost earlier. The sublimation would create significant outgassing pressure. Gas escaping from the nucleus would carry dust particles with it, forming a growing coma around the comet. The coma would expand as more material was released. At 0.3 astronomical units, approaching Mercury's distance, the heating would be intense enough to cause rapid mass loss. The surface would be sublimating ice at a rate potentially measured in meters per day. The outer layers of the nucleus would be eroding away continuously. The structure would begin to weaken. As ice sublimates from the surface and from cracks and pores in the interior, the structural integrity would degrade. The nucleus was probably never very strong, being a loosely consolidated mixture of ice and dust rather than a solid block. The heating wouldn't be uniform. The side facing the sun would heat much more than the opposite side, creating thermal stresses. Different areas with different compositions would respond differently, creating uneven sublimation and potentially causing fragmentation. At 0.2 astronomical units, the solar flux would be 25 times Earth's level. Surface temperatures would exceed the melting point of water ice. But in vacuum, ice doesn't melt. It sublimates directly from solid to gas. The rate would be extraordinary. The outgassing would create significant non-gravitational forces on the nucleus. The rocket effect from sublimating ice would push the comet, slightly altering its trajectory. For most comets, this is a small effect, but with the extreme sublimation rates in a close approach, the forces could be substantial. The coma would be enormous, potentially millions of kilometers across. The released gas and dust would be pushed by solar radiation pressure and the solar wind, forming a tail that extended behind the comet along its orbital path. But the tail would look different from typical cometary tails. The extreme solar wind close to the sun would push material with greater force. The magnetic fields might affect ionized gas in the tail, creating spectacular curved structures. At 0.1 astronomical unit, just a tenth of Earth's distance from the sun, the situation would become catastrophic for the comet. The solar flux would be 100 times Earth's level. Surface temperatures would reach hundreds of degrees Celsius. Ice wouldn't sublimate slowly. It would explode off the surface as thermal energy pumped into the nucleus faster than it could be conducted away. The surface would be a roiling chaos of erupting gas jets and crumbling structure. The dust released would be heated to high temperatures by solar radiation, potentially glowing visibly from its own thermal emission. The comet would be surrounded by a cloud of hot gas and glowing dust, making it appear much larger and brighter than its actual nucleus. Observations from Earth or spacecraft would show a brilliant object growing rapidly brighter as it approached the sun. The brightness would increase according to a predictable formula based on distance and activity rate, though the extreme conditions might cause behaviour outside normal patterns. The nucleus itself would be shrinking visibly. If it started at 3 kilometers diameter, it might lose hundreds of meters of radius during the approach. The mass loss would be substantial, potentially tons per second of material streaming away. The internal structure would be under tremendous stress. Heat would be conducting inward from the superheated surface. Interior ice would be warming and sublimating, creating pressure that could cause the nucleus to crack or explode. Some comets have been observed to fragment during close solar approaches, breaking into multiple pieces that separate and follow slightly different orbits. The thermal stress combined with weakened structure from rapid sublimation makes fragmentation common for sungrazing comets. The comet was approaching a point of no return. The closer it got, the more inevitable its destruction became. Physics allowed no escape once inside a certain distance. The sun's energy was simply too overwhelming for such a fragile object to withstand. Beyond heating, 3I/Atlas would experience another destructive force as it approached the sun. Tidal effects from the sun's immense gravitational field. Tidal forces arise from the gradient in gravitational field strength. The side of an object closer to a massive body experiences slightly stronger gravity than the far side. This differential creates a stretching force that tries to pull the object apart. Earth experiences tidal forces from the moon and sun, creating ocean tides. The solid Earth also deforms slightly, bulging toward and away from the moon. But Earth is rigid enough and far enough from these bodies that tidal forces are small, just enough to move water and flex the crust slightly. For a comet approaching very close to the sun, tidal forces would be far more significant. The sun's mass is enormous, and at close distances the gravitational gradient is steep. The Roche limit is the distance inside which tidal forces from a massive body overcome the self-gravity holding a smaller body together. For a rigid body orbiting the sun, the Roche limit is at about 2.4 solar radii from the sun's centre, about 1.7 million kilometres. But comets aren't rigid. They're loosely consolidated rubble piles held together by weak ice cohesion and self-gravity. For such weak bodies, the effective Roche limit is larger, perhaps 3 to 4 solar radii, roughly 2 to 3 million kilometres from the sun's centre. If 3I/Atlas approached to within this distance, tidal forces would begin tearing it apart regardless of heating effects. The gravitational difference between the sun-facing side and the far side would exceed the comet's internal strength. The disruption would happen gradually at first. The nucleus would deform, elongating along the line toward the sun. If it was rotating, the rotation would complicate the deformation, potentially causing tumbling or chaotic orientation changes. As tidal stress increased with closer approach, cracks would form. The loosely consolidated structure would fragment along weak planes. Pieces would begin separating, each following a slightly different orbit based on its position and velocity when it broke free. The result would be a spreading cloud of fragments rather than a single nucleus. The fragments would continue toward perihelion but along diverging paths. The closest fragments to the Sun during disruption would have slightly different perihelion distances than those farther away. Some fragments might be pulled into paths that take them even closer to the Sun, while others might be flung to larger perihelion distances. The gravitational interaction during disruption would redistribute orbital energy among the pieces. This tidal disruption process has been observed in sungrazing comets. Some comets have been seen to fragment near the Sun, creating spectacular displays as the pieces separate and each develops its own coma and tail. Comet Shoemaker-Levy 9 experienced tidal disruption when it passed too close to Jupiter in 1992. The comet broke into at least 21 fragments that strung out along its orbit. Those fragments later impacted Jupiter in July of 1994, creating the famous series of impact scars. The disruption of 3I/Atlas near the Sun would be even more violent than Shoemaker-Levy 9's breakup, because the Sun's tidal forces are stronger than Jupiter's, and the comet would be experiencing simultaneous extreme heating. The combination of tidal stress and thermal stress would weaken the structure from multiple directions. Thermal stress would create cracks and weak zones. Tidal stress would pull along those weaknesses, accelerating fragmentation. As pieces separated, they would each begin sublimating vigorously on their own. Smaller pieces have higher surface-to-volume ratios, meaning they heat up faster and lose mass more quickly relative to their size. The fragment cloud would rapidly evolve. Within hours of disruption, the smallest pieces might sublimate completely, vanishing into gas and dust. Medium-sized pieces would shrink dramatically. Only the largest fragments, if any existed, might remain partially intact. The gravitational dynamics of the fragment cloud would be complex. Each piece would technically be in its own orbit around the Sun, but the pieces would be close enough to exert gravitational influence on each other. These mutual gravitational effects would be small compared to the Sun's gravity, but could cause subtle changes in the fragment's orbits. Pieces might collide with each other, merging or shattering. The cloud would spread along the orbital path. From Earth, observing this process would be challenging but potentially spectacular. Telescopes would see the comet suddenly brighten as fresh surface area was exposed by fragmentation. Multiple condensations would appear in the coma, each trailing its own faint tail. Spectroscopy might reveal composition differences between fragments if different pieces came from different parts of the original nucleus, with different compositions. This would provide rare insight into the internal structure and composition of an interstellar comet. The tidal disruption would seal the comet's fate, even if heating alone might have allowed some survival. Once broken into pieces, the fragments would be far more vulnerable to solar radiation and wouldn't have enough mass to hold themselves together through perihelion. The question would shift from quote 0 to quote 1. The answer would depend on exactly when and how the disruption occurred. If disruption happened far enough from the Sun, perhaps at 3 or 4 solar radii, the fragments might survive long enough to pass perihelion before completely sublimating. Some fragment material might escape back to interstellar space. But if disruption occurred closer, at 2 solar radii or less, the fragments would likely sublimate completely before or shortly after perihelion. Nothing solid would survive to continue the outbound journey. Tidal forces would thus work together with heating to ensure 3I/Atlas's destruction in a close solar approach. The comet would be attacked simultaneously by the Sun's energy tearing away its surface and the Sun's gravity pulling apart its structure. Against such dual assault, a loosely consolidated 3-kilometre ice ball had essentially no chance of survival. The question wasn't if it would be destroyed, but exactly how and when the destruction would occur as it plunged toward its fiery fate. The moment of closest approach, perihelion, would be the climax of 3I/Atlas's death spiral into the Sun's influence, the point where all the destructive processes reach their maximum intensity. If we imagine the comet somehow remaining intact until perihelion despite the heating and tidal forces discussed earlier, the conditions at closest approach would depend critically on exactly how close Quote 2 was. Let's consider several scenarios with different perihelion distances to understand the range of possible outcomes. At 0.05 astronomical units, about 7.5 million kilometers from the Sun's centre, roughly 10 solar radii, the comet would experience solar flux about 400 times Earth's intensity. The surface temperature would reach over 700 degrees Celsius. At this distance, tidal forces would still be below the Roche limit for complete disruption, but the heating would be catastrophic. The nucleus would be sublimating ice at rates of many tons per second. The coma would be enormous and brilliant. The passage through perihelion would be brief. At the high velocity typical of a sun-grazing orbit, the comet might spend only a few hours within 0.1 astronomical unit of the Sun. But those hours would see tremendous mass loss. If the nucleus was 3 kilometers diameter initially, it might lose several hundred meters of radius during the perihelion passage alone. The surface would be eroding at meters per minute. The interior would be heating, potentially causing explosive outbursts as subsurface ice vaporized. The comet would be at its brightest, visible even in daylight from Earth if viewing geometry was favourable. The magnitude might reach 0 or brighter, rivaling the brightest stars despite being lost in the Sun's glare. At 0.02 astronomical units, about 3 million kilometres, roughly 4 solar radii, the conditions would be even more extreme. This is approaching the tidal Roche limit for a weak body like a comet. The solar flux would be about 2,500 times Earth's intensity. Surface temperatures would exceed 1,000 degrees. Silicate dust would be melting or vaporizing. Only the most refractory materials like certain metals would remain solid at such temperatures. Tidal forces would be straining the nuclear structure. If it hadn't already fragmented from thermal stress, it likely would fragment now from tidal stress. The nucleus would elongate visibly, pulling apart along the sun-facing axis. The sublimation rate would be so high that the outgassing would create significant pressure affecting the comet's orbit. The trajectory might deflect noticeably from pure gravitational motion due to the rocket effect. The coma would glow from its own heat, not just reflected sunlight. Hot dust would emit thermal radiation in the visible spectrum. The comet might appear orange or red from the glowing material surrounding it. At 0.01 astronomical unit, about 1.5 million kilometres, roughly 2 solar radii, the comet would be inside the tidal Roche limit. Tidal disruption would be inevitable. The nucleus would be pulled into a string of fragments within minutes or hours. The solar flux would be 10,000 times Earth's intensity. Temperatures would exceed 2,000 degrees. Almost all materials would be vaporizing. The distinction between nucleus and coma would blur as everything turned to hot gas and plasma. The fragments from tidal disruption would each be heating and sublimating explosively. The fragment cloud would expand rapidly, not just from orbital mechanics, but from the pressure of vaporizing material pushing pieces apart. From Earth, if observations were possible through the sun's glare, telescopes would see a brilliant elongated streak, possibly changing brightness rapidly as fragments sublimated and released bursts of material. The spectroscopic signature would show highly ionized atoms, evidence of the extreme temperatures. At 0.005 AU, essentially at the sun's surface, the comet would be in the corona itself. The conditions would be so extreme that calling it a Quote 3 would be misleading. It would be a cloud of vaporizing rock and ice plunging into million-degree plasma. The solar flux directly from the photosphere below would be about 60 million watts per square metre. The coronal plasma around the comet would be over 1 million degrees. Though the low density means the heat transfer would be less than you might expect. but the radiation flux alone would vaporize anything. There would be no solid nucleus, no ice, no rock. Everything would be plasma, ionized atoms stripped of electrons. The material from 3I/Atlas would mix with the solar corona, indistinguishable from the Sun's own atmosphere. But from the comet's perspective, the perihelion passage would be the ultimate dissolution. Everything that made 3I/Atlas a discrete object, its structure, composition, identity, would be stripped away and scattered into the Sun's atmosphere. If any material survived perihelion, it would only be the smallest particles of the most refractory dust, blown outward by radiation pressure. These tiny grains, microscopic silicate crystals perhaps, might escape on hyperbolic trajectories, continuing into interstellar space as remnants of a comet that died visiting a star. The perihelion passage would thus represent the final transformation of 3I/Atlas, from interstellar visitor to solar system debris, and ultimately to atoms merged with the Sun itself. The journey from distant cold to stellar fire would be complete. The exact details would depend on the precise perihelion distance, the comet's approach velocity, its structural strength, and other factors. But the overall pattern would be the same: increasing destruction culminating in complete disintegration at closest approach. There would be beauty in the destruction. The physics playing out would be fundamental processes of heat, gravity, and matter responding to extreme conditions. Understanding these processes helps us comprehend not just comets, but the nature of materials and forces throughout the universe. As 3I/Atlas approached perihelion in our hypothetical close encounter, fragmentation wouldn't be a single event, but a cascade of breakups at multiple scales, creating a complex evolution from one nucleus to countless pieces. The cascade would begin far from the Sun, possibly at several astronomical units distance, with small pieces breaking off from the main nucleus. These early fragments would be caused by thermal stress as the comet began warming, creating differential expansion that cracked weak areas. These initial fragments would be relatively large, perhaps tens to hundreds of meters across. They would separate slowly from the parent nucleus, their slightly different velocities causing them to drift apart over days and weeks. Each fragment would follow a slightly different orbit, though initially all orbits would be very similar. The differences would accumulate over time, causing the fragment cloud to spread along the orbital path. As the comet continued toward the Sun and heating intensified, the fragmentation rate would increase. The main nucleus might shed fragments continuously, like a disintegrating spacecraft losing pieces as it falls apart. Some fragments would break off gently, drifting away slowly. Others would be ejected violently by outgassing pressure from localized sublimation eruptions. These ejections could give fragments significant velocity relative to the nucleus, several meters per second or more. At around 0.5 to 0.3 astronomical units, thermal stress would become severe enough to cause major fragmentation events. The main nucleus might split into several large pieces, perhaps creating 2 or 3 secondary nuclei each a kilometer or more across. This major fragmentation would dramatically change the comet's appearance. Instead of one bright condensation in the coma, observers would see multiple bright spots, each surrounded by its own mini-coma of released gas and dust. The secondary nuclei would continue inward, each fragmenting further as heating increased. A hierarchical pattern would emerge, large pieces breaking into medium pieces breaking into small pieces breaking into tiny fragments. The fragment size distribution would probably follow a power law, many small pieces and few large ones. This pattern is common in fragmentation processes and results from the physics of how materials break under stress. As fragments got smaller, their surface-to-volume ratio increased. This meant they heated faster relative to their size and sublimated more quickly. The smallest fragments, meters or tens of meters across, would have lifetimes of hours once inside 0.2 astronomical units. These small fragments would create brief bright flares as they disintegrated. Observers might see sudden brightness increases as a fresh fragment with new surface area began vigorously sublimating before fading as it eroded away to nothing. The cascade would accelerate as the comet approached 0.1 astronomical unit. At this point, thermal stress alone would be sufficient to disintegrate any remaining large pieces. Even if structural integrity had kept the nucleus together until now, it would fail here. Pieces that had been held together by weak ice cohesion would separate. The ice acting as cement between dust grains would sublimate, leaving only loose dust that would drift apart. Coherent fragments would transition to diffuse clouds of individual particles. The tidal forces, if the approach was close enough, would add to the fragmentation cascade. As the comet crossed inside 3 to 4 solar radii, tidal stress would pull pieces apart even if they might otherwise have held together. The tidal disruption would preferentially affect the largest remaining pieces. Big fragments would experience the strongest tidal gradients and would be pulled into elongated shapes before breaking. Smaller pieces would be less affected by tides, but more affected by their own sublimation. By perihelion, if the approach was very close, there might be no solid pieces larger than perhaps tens of meters, and even those would be fragmenting continuously. The quote 4 would have become a stream of debris, a trail of particles and fragments spread along the orbit. The spatial distribution of fragments would be complex. Pieces broken off early in the approach would be spread over millions of kilometers along the orbit. Pieces breaking off near perihelion would be more tightly clustered. Those remnants would continue on hyperbolic trajectories out of the solar system, carrying forward a fraction of 3I/ATLAS's original mass. Most of the comet would have been left behind, vaporized into gas and dust scattered through the inner solar system. The fragmentation cascade would thus transform one coherent interstellar visitor into a scattered population of particles, a transition from object to debris field, from comet to cosmic dust. The cascade itself would be the mechanism of death, breaking down structural integrity until nothing solid remained. As 3I/Atlas fragmented and sublimated, it would release enormous amounts of dust that would create a spectacular tail visible from Earth, if observation geometry allowed, providing a visible record of the comet's destruction. Cometary dust is released when sublimating ice carries solid particles embedded in it away from the nucleus. The dust particles are typically silicate minerals, organic compounds, and sometimes metallic grains. Ranging in size from nanometers to millimeters, these structures would evolve over time. The different sized dust particles would be pushed by radiation pressure at different rates. Large particles, millimeters across, would barely be affected and would essentially continue on their orbital paths. Small particles, microns across, would be strongly pushed by radiation pressure and would be accelerated away from the Sun. The smallest particles could reach velocities exceeding the comet's orbital velocity, being essentially blown out of the solar system by light. This size-dependent separation would cause the tail to spread into a fan shape. Different size particles would follow different trajectories, creating a gradation from the orbital path of the largest particles to the radial paths of the smallest particles pushed directly away from the Sun. The dust particles themselves would be affected by the intense solar radiation. The smallest particles would heat to hundreds or thousands of degrees, depending on composition and distance from the Sun. Dark, carbonaceous particles would absorb more radiation and heat more than bright reflective silicate grains. The hot dust would emit thermal radiation, glowing visibly in the optical and infrared. Near perihelion, the dust tail might actually be self-luminous, not just reflecting sunlight but emitting its own light from thermal radiation. The tail would glow orange or red from the heated dust, creating a spectacular appearance. Some dust particles, particularly those passing very close to the Sun, would heat enough to vaporize. Silicate grains at 0.01 astronomical unit would reach temperatures above their sublimation point. These particles would turn to gas, adding to the atomic and molecular components of the tail. The vaporized dust would contribute ions to the ion tail, a separate tail structure composed of ionized gas. The ion tail forms when solar ultraviolet radiation ionizes gas molecules, and the solar wind's magnetic field pushes the ions away from the Sun. 3I/Atlas would have both a dust tail and an ion tail, with the ion tail appearing straighter and often bluer than the dust tail due to emission from ionized molecules. Near the Sun, the ion tail might be particularly active and bright due to the intense radiation ionizing the abundant gas released by the disintegrating nucleus. The interaction between dust and gas would be complex. Gas drag, the friction between sublimating gas and dust particles, would affect how dust was released from the nucleus. Rapidly expanding gas could carry dust particles along, accelerating them. Different dust compositions would behave differently. Organic compounds might vaporize at lower temperatures than silicates, creating composition-dependent effects in the tail. Spectroscopy could potentially identify different minerals and compounds by their emission signatures. The tail evolution would also reflect the changing solar wind and magnetic field conditions as the comet travelled through different regions near the Sun. The solar wind is variable, with different densities and velocities at different times and locations. If the comet passed through a coronal mass ejection or a region of strong magnetic field, the tail structure might be dramatically affected. The ion tail could show kinks or disconnection events where magnetic field changes altered the ion flow patterns. From Earth, monitoring the tail's evolution would provide a time-lapse record of the comet's destruction. Observations taken hours or days apart would show how the tail grew, developed structure, and evolved as fragmentation and sublimation proceeded. The tail would reach maximum extent and brightness around perihelion when dust release peaked. After perihelion, as the comet moved away from the Sun and fragmentation slowed, the tail would gradually fade and eventually dissipate. But the dust released during the perihelion passage wouldn't disappear immediately. It would continue orbiting the Sun, gradually spreading into a diffuse stream along the comet's former orbital path. Some of this dust might eventually be swept up by planets or fall into the Sun over thousands or millions of years. The dust tail would thus be both a visible manifestation of the comet's death and a legacy that would persist long after the nucleus itself had vanished. It would be the most spectacular aspect of the close approach, the feature most likely to be visible from Earth and most easily photographed. If 3I/Atlas had approached very close to the Sun, its tail might have rivaled or exceeded the great comets of history in brightness and extent. It could have been a once-in-a-lifetime spectacle, a brilliant display of cosmic destruction visible even in the daytime sky. Beyond the dust and neutral gas, 3I/Atlas, passing very close to the Sun, would experience intense ionization effects, transforming much of its material into plasma and creating complex electromagnetic interactions with the solar environment. Ionization occurs when atoms or molecules lose electrons, becoming electrically charged ions. This can happen through several mechanisms, all of which would be operating at high intensity near the Sun. Photoionization, caused by high-energy ultraviolet and X-ray photons from the Sun, would be the primary ionization mechanism for most of the gas released by the comet. Solar UV radiation is intense near the Sun, easily providing enough energy to knock electrons off atoms and molecules. The coma would develop a bow shock, a region where the solar wind slows down as it encounters the obstacle of the dense cometary gas. Behind the shock would be a region where the solar wind is deflected around the coma. The comet's ionized gas would be picked up by the solar wind and carried away from the Sun, forming the ion tail. This process would be particularly intense close to the Sun where the solar wind density and velocity are high. The ion tail would be visible through emission lines from ionized molecules. Carbon monoxide ion, water ion, and other species would emit characteristic colours as they recombine with electrons or transition between energy states. Close to the Sun, the ionization fraction would be very high. Most of the gas released by the comet would be ionized within seconds to minutes. The coma would be essentially a cloud of plasma, partially ionized gas consisting of ions and free electrons. This plasma would interact with the Sun's magnetic field in dynamic ways. Magnetic field lines could be dragged by the moving plasma, compressed and reconnected. These magnetic interactions could heat the plasma and accelerate particles. In the most extreme case, if 3I/Atlas passed through a solar prominence or active region with very strong magnetic fields, the interactions could be violent. The comet plasma could be shaped by magnetic forces, potentially creating narrow jets or filaments aligned with field lines. Coronal mass ejections, if one occurred near the comet's location, would engulf the coma in a blast of fast-moving plasma with embedded magnetic fields. The comet material would be swept along with the CME, mixing with the solar plasma. The energetics of these interactions would be substantial. The kinetic energy of the fast-moving solar wind impacting the comet's dense coma would heat and compress the cometary plasma. Some particles might be accelerated to high energies, creating beams of fast ions. These energetic particles could produce X-ray emission through collisions and other processes. Spacecraft with X-ray telescopes observing the inner solar system might detect X-rays from the comet, a signature of the violent electromagnetic environment. The ionization would also affect the comet's spectrum dramatically. Instead of the usual molecular emission lines seen in comets far from the Sun, the spectrum would be dominated by atomic and ionic lines from highly excited atoms. Spectroscopic observations would show lines from ionized carbon, oxygen, silicon, iron and other elements present in cometary material. The ionization stages would indicate the temperature and radiation field intensity, providing diagnostics of the conditions. The ratio of different ions would change with distance from the Sun, reflecting changing radiation intensity and collisional ionization rates. By tracking these spectroscopic changes, scientists could study the physical conditions the comet experienced. The magnetic field effects would also potentially be detectable. The ion tail structure and orientation would reveal the magnetic field direction. Kinks and waves in the tail would show magnetic disturbances caused by field line reconnection or solar wind variations. If spacecraft were in the inner solar system during the comet's passage, they might detect radio emissions from the plasma interactions. Shock waves and magnetic reconnection can generate radio waves through various plasma physics mechanisms. The electron density in the coma could be measured through radio observations. Spacecraft radio signals passing through the coma would be affected by the free electrons, allowing measurement of the electron column density. All of these ionization and plasma effects would essentially transform 3I/Atlas from a simple ice and rock object into a complex plasma physics phenomenon. The comet would become a temporary active region in the solar atmosphere, a localized plasma structure interacting with the background solar environment. The ionization effects would be most intense at perihelion, but would extend far along the comet's path. The ion tail could stretch for tens or hundreds of millions of kilometers, carrying ionized material from the destroyed nucleus deep into interplanetary space. Eventually, far from the Sun, the ions would recombine with electrons, becoming neutral atoms again. These neutral atoms would continue on trajectories shaped by their acceleration in the inner solar system, spreading through the solar system and potentially escaping to interstellar space. The ionization effects would thus mediate how material from 3I/Atlas was dispersed and where it ended up. Ions behaved differently from neutral particles, being pushed by electromagnetic forces rather than just gravity and radiation pressure, affecting the ultimate distribution of comet material throughout space. Observing 3I/Atlas during a very close solar approach would present extraordinary challenges for astronomers, making detailed study difficult despite the spectacular nature of the event. The fundamental problem is that the sun is extremely bright. Looking at anything close to the sun requires either blocking the sun's light or observing at times and geometries where the sun is not in the field of view. For a comet passing inside 0.1 astronomical unit, it would be lost in the sun's glare from Earth's perspective. The angular separation from the sun would be small, perhaps only a few degrees or less. Observing an object that close to the sun is nearly impossible with ground-based telescopes during daylight. Specialized solar telescopes with coronagraphs, devices that block the sun's disk to allow observation of the faint corona, could potentially observe a bright comet passing near the sun. Several spacecraft carry coronagraphs for solar observation. The Solar and Heliospheric Observatory, SOHO, has discovered thousands of sungrazing comets using its coronagraph instruments. These observations show comets as bright spots moving through the field of view, appearing on one side of the occulting disk and disappearing on the other. For 3I/ATLAS, SOHO, and similar spacecraft would provide the best observations during close approach. The LASCO coronagraph on SOHO can observe from about 1.5 to 30 solar radii from the sun's centre, covering the range where the comet would be most interesting. But coronagraph observations have limitations. They provide relatively low spatial resolution compared to large ground-based telescopes. Fine details of the nucleus fragmentation might not be resolved. The observations would show the overall coma and tail structure, but not small fragments. The temporal resolution would also be limited by how frequently images are taken. If the comet is moving rapidly through the field of view, sparse imaging might miss brief events like fragment outbursts. Spectroscopic observations near the sun are even more challenging. Most coronagraphs are designed for imaging, not spectroscopy. Getting detailed spectroscopic data of the comet's composition and physical conditions would be difficult. Some spacecraft do carry spectrographs capable of observing in the inner solar system. The Parker Solar Probe, launched in 2018 to study the sun up close, has instruments that could potentially detect a comet if one passed through its observation region. But Parker Solar Probe wasn't designed for comet studies, and its instruments might not be optimally configured for observing cometary phenomena. The observations would be serendipitous rather than planned. Ground-based observations would be possible when the comet was far enough from the sun to be observed in a dark sky, either before perihelion during pre-dawn observations or after perihelion during evening observations. The challenge is timing. If the perihelion distance is very small, the comet might only be observable from Earth when it's still relatively far from the sun, perhaps beyond 0.5 astronomical units. By the time it reaches the most interesting phase near perihelion, it would be too close to the sun to observe. After perihelion, if anything survived, ground-based telescopes might reacquire the comet as it emerged from the sun's glare. But if the nucleus was destroyed during perihelion passage, there might be little left to observe. The debris cloud would be diffuse and faint, difficult to detect against the bright sky near the sun. Only the largest fragments or the densest parts of the dust tail might be visible. Radio observations might be possible throughout the passage. Radio telescopes can observe during daytime and can point close to the sun without the same glare problems that affect optical telescopes. The rapid evolution during close approach compounds this problem. Changes that would take weeks for a normal comet might happen in hours near the sun. Continuous monitoring would be ideal but practically difficult. Data analysis would also be challenging. The extreme conditions and complex physics mean that interpreting observations requires sophisticated modelling. Distinguishing between different physical processes from limited data would be difficult. For example, determining whether observed fragmentation was caused by thermal stress, tidal forces, or some combination would require detailed modelling of the comet's structure and orbit, combined with precise timing of when fragments appeared. Despite all these challenges, observing 3I/Atlas during close solar approach would be scientifically invaluable. Such events are rare, and each provides unique data about comet physics under extreme conditions. The observations would test models of cometary behaviour, provide information about composition and structure, and reveal how materials behave under conditions rarely encountered in the solar system. The scientific community would make every effort to observe as comprehensively as possible, coordinating spacecraft, ground-based observatories, and amateur astronomers to capture as much data as the observational constraints allowed. The result would be an incomplete but fascinating data set, pieces of a puzzle that scientists would work to assemble into a coherent picture of the comet's death, using the limited observations to infer the unobservable details through physical modelling and reasoning. After examining all the destructive processes that would affect 3I/ATLAS during a close solar approach, the natural question is, could anything survive? Would any part of the comet make it through perihelion and escape back to interstellar space? The answer depends critically on the perihelion distance. For approaches outside about 0.1 astronomical unit, survival of at least some material is likely. Many comets pass perihelion at such distances and survive, though with substantial mass loss. At 0.05 astronomical units, survival becomes questionable. The extreme heating and potential tidal disruption make it unlikely that any coherent nucleus would remain, but the largest fragments might partially survive as smaller bodies. Inside 0.02 astronomical units, survival of anything larger than dust particles becomes very unlikely. The conditions are simply too extreme for solid ice or rock to endure. Complete sublimation or vaporization would be the probable outcome, but even if the nucleus is completely destroyed, not all the material would fall into the sun. Much of it would be blown outward by radiation pressure and solar wind, escaping on hyperbolic trajectories. The smallest dust particles, microns in size, would be particularly strongly affected by radiation pressure. They could be accelerated to velocities exceeding solar escape velocity, carrying them completely out of the solar system and back into interstellar space. These tiny particles would be all that remained of 3I/Atlas in a very close approach. Microscopic silicate grains and perhaps some refractory organics, scattered through space as reminders of a comet that came too close to the sun. The question of chemical survival is also interesting. Even if all solid material is destroyed, the atoms that made up the comet would continue to exist, just in atomic or ionic form rather than molecular. Hydrogen from water would eventually escape to space, too light to be held by the sun's gravity. Oxygen might become ionized oxygen in the corona or solar wind. Carbon, nitrogen, silicon, iron, and other elements would mix with solar material or escape in the solar wind. In this sense, 3I/Atlas would achieve a kind of immortality, its constituent atoms becoming part of the sun or dispersing through the solar system and beyond, perhaps someday being incorporated into new worlds or objects. For comparison, we can look at historical sungrazing comets to understand survival statistics. The Kreutz family of sungrazers, believed to be fragments of a larger comet that broke apart centuries ago, includes many comets that pass very close to the sun. Some Kreutz comets have perihelion distances of only a few solar radii, well inside 0.01 astronomical unit. Most of these comets don't survive perihelion. They're observed approaching the sun by SOHO's coronagraph, but don't appear on the other side. The interpretation is that these comets sublimate completely during perihelion passage, their material dispersed into gas and dust. Nothing solid emerges from their closest approach, but occasionally Kreutz comets do survive, at least partially. They appear on both sides of the sun in coronagraph images, indicating that some material made it through perihelion, though the nucleus after perihelion is usually much smaller and fainter than before. The survival seems to depend on the comet's size and composition. Larger comets have more mass to ablate and can survive longer under extreme heating. Comets with more refractory material, perhaps higher rock-to-ice ratios, are more durable than pure ice. 3I/Atlas, at roughly 3 kilometers diameter initially, would be relatively large compared to typical Kreutz comets. which are often only tens to hundreds of meters across. This larger size would improve survival chances, but the interstellar composition might be different from solar system comets. If 3I/Atlas had higher ice content or lacked the refractory materials common in inner solar system comets, it might be more fragile. The approach velocity also matters. Faster comets spend less time in the most intense environment near perihelion. 3I/ATLAS, coming from interstellar space, would have high velocity, minimizing time near the Sun. A rough calculation: at 0.05 astronomical units perihelion distance, with a perihelion velocity of perhaps 400 kilometers per second, the comet would spend only about 2 hours within 0.1 astronomical units of the Sun. In those 2 hours, how much mass could sublimate? The sublimation rate depends on surface area, solar flux, and ice properties. For a 3-kilometer sphere, the surface area is about 30 square kilometers. At 0.05 astronomical units, the solar flux is about 400 times Earth's solar constant, roughly 500,000 watts per square meter. Total energy input would be on the order of 10 to the 13th watts. Ice sublimation requires about 3 million joules per kilogram. With 10 to the 13th watts, you could sublimate about 3 million kilograms per second, or roughly 10 billion kilograms over 2 hours. The total mass of a 3-kilometer comet with typical density would be on the order of 10 to the 13th kilograms, 10 trillion. Losing 10 billion kilograms, 10 to the 10th, would be less than 1% of the total mass. This crude calculation suggests that the comet might survive, at least most of its mass, if structural integrity held and if it didn't fragment into smaller pieces that would sublimate faster. But this calculation ignores fragmentation, tidal effects, and the fact that sublimation accelerates as surface area increases from structural disruption. In reality, survival would be more marginal than this simple estimate suggests. The most likely outcome for a very close approach would be partial survival. The nucleus fragments. Most fragments sublimate completely, but the largest few fragments partially survive and escape as much smaller bodies, perhaps tens or hundreds of meters across instead of kilometers. These remnants would continue on hyperbolic trajectories, leaving the solar system. They would carry away some fraction of 3I/Atlas's original mass, perhaps 1% or less, with the rest lost to sublimation and dispersal. Those remnants would be interesting scientifically. They would have survived conditions rarely experienced by natural objects. Their surfaces would be heavily processed, transformed by extreme heating. Their interiors might preserve less altered material protected by the ablated outer layers. If we could somehow sample those remnants, they would provide unique information about both the original interstellar comet and the effects of extreme solar environment on cometary materials. But the remnants would be small, dark, and rapidly receding from the Sun on a hyperbolic trajectory. Detecting them would be challenging. They might escape notice entirely, leaving us to wonder whether anything survived or whether 3I/Atlas was completely destroyed. The survival question would thus likely remain partially unresolved. Another uncertainty in a scenario already full of unknowns, a question about whether the comet's story ended completely at perihelion or whether diminished remnants carried a fraction of it back to the cosmic dark. Understanding what would happen to 3I/ATLAS requires understanding the thermal physics, how heat flows and what happens to materials at extreme temperatures. Heat transfer occurs through 3 mechanisms: conduction, convection, and radiation. For a comet in space, convection is irrelevant since there's no atmosphere. The relevant processes are radiation absorption from the Sun, thermal radiation emission from the comet, and conduction within the comet's structure. The energy balance is conceptually simple. The comet absorbs solar radiation on its sunlit side. It emits thermal radiation from its entire surface. The difference between absorbed and emitted energy determines whether the comet heats up or cools down. In equilibrium, Absorption equals emission. The temperature adjusts until the emitted power equals the absorbed power. This equilibrium temperature depends on the solar flux and the comet's surface properties. For a black body which absorbs all radiation and emits according to the Stefan-Boltzmann law, the equilibrium temperature at Earth's distance is about 280 Kelvin, roughly 7 degrees Celsius. This is the temperature an object in space at 1 astronomical unit would reach. Real surfaces aren't perfect black bodies. They have albedo, the fraction of light they reflect, and emissivity, the efficiency of thermal emission compared to a black body. For comet nuclei, typical albedos are low, around 0.04, meaning they absorb 96% of incident light. At 0.39 AU 3I/ATLAS's actual perihelion distance, the equilibrium temperature would have been about 450 Kelvin, 177 Celsius, hot enough that water ice sublimes rapidly. At closer distances, temperatures rise dramatically. At 0.1 astronomical unit, equilibrium temperature would reach about 900 Kelvin, 627 Celsius. At 0.05 astronomical units, roughly 1270 Kelvin, almost 1000 Celsius. But equilibrium assumes the surface has time to adjust its temperature. During rapid close approach, the actual surface temperature might lag behind equilibrium because thermal conduction into the interior and energy consumption by sublimation prevent the surface from heating as quickly as equilibrium predicts. The thermal conduction into the comet's interior is limited by the thermal conductivity of cometary material. Ice and rock are relatively poor conductors. Heat doesn't penetrate quickly, meaning the interior can remain cold while the surface is extremely hot. This creates steep temperature gradients. The outer few centimetres might be at hundreds or thousands of degrees, while a metre beneath the surface remains at only tens of degrees above absolute zero. The thermal gradient causes mechanical stress. Material expands when heated. If the surface is hot and expanded while the interior is cold and contracted, stress builds up in the structure. This thermal stress can cause cracking and fragmentation. Sublimation consumes energy, providing a cooling mechanism that moderates surface temperature. When ice sublimes, it absorbs latent heat, about 3 million joules per kilogram for water ice. This energy comes from the surface heat, cooling it. For intense solar radiation, sublimation can be the dominant energy sink. Most of the absorbed solar energy goes into sublimating ice rather than heating the surface. This is why sublimation rates correlate with solar flux. More flux means more energy available for sublimation, but sublimation has limits. Once all the ice in the surface layers is gone, leaving only refractory dust and rock, sublimation cooling stops. The remaining material heats to much higher temperatures than ice-rich surfaces could reach. This creates a feedback effect. As surface ice sublimates away, the surface gets hotter, which might cause deeper ice to sublimate faster, which removes more ice, leading to even higher temperatures. The surface can undergo runaway heating and mass loss. Different ices sublimate at different temperatures. Water ice is relatively stable compared to more volatile ices like carbon dioxide and carbon monoxide. In our solar system comets, the more volatile ices sublimate first, at larger solar distances, leaving water ice to dominate close to the Sun. 3I/Atlas likely had similar composition stratification. By the time it reached very close to the Sun, the most volatile ices would already be gone from surface layers. The mass loss during close approach would be primarily water ice and refractory material. The refractory material, rock and dust, doesn't sublimate until temperatures exceed roughly 2000 Kelvin. At 0.05 astronomical units, surface temperatures might not quite reach that level due to cooling from ice sublimation. But at closer approaches, say 0.02 astronomical units, refractory material would start vaporizing. Silicon, iron, magnesium, and other rock-forming elements would become gaseous. The comet would be losing not just ice but rock, transforming completely to vapor. The vaporization of refractory materials requires much more energy than ice sublimation. The latent heat of vaporization for silicate minerals is about 10 million joules per kilogram, more than 3 times that of water ice. This means that vaporizing rock provides even more cooling than sublimating ice per unit mass. But it also means that rock vapor represents an enormous energy input, indicating just how intense the solar radiation is at very close distances. The thermal physics thus determines how quickly 3I/Atlas would be destroyed and what would happen to the material. At moderate perihelion distances, ice sublimation dominates. At very close distances, even rock vaporizes. The outcome depends on which thermal regime the comet enters. Understanding these thermal processes allows quantitative modelling of mass loss rates, temperature distributions, and survival prospects for different approach scenarios. The models aren't perfect. They require assumptions about material properties that aren't well known, but they provide frameworks for understanding what physics tells us should happen. The orbital mechanics of 3I/Atlas's close approach would determine the timeline and geometry of the encounter, shaping how long the comet spent in extreme conditions and what path it followed. Orbital motion follows Kepler's laws, generalized by Newton into the universal law of gravitation. An object's trajectory around the Sun is determined by its position and velocity at any given time, plus the Sun's gravitational pull. For 3I/Atlas, entering the solar system from interstellar space, the trajectory would be hyperbolic. Hyperbolic orbits are unbound, meaning the object has more than enough energy to escape the Sun's gravity. The excess energy, called hyperbolic excess velocity, would be apparent far from the Sun where the object's speed approached a constant value. For 3I/Atlas, this value was calculated at roughly 34 kilometers per second based on actual observations. As the comet approached the Sun, it would accelerate under gravitational attraction. At perihelion, closest approach, it would reach maximum velocity. After perihelion, it would decelerate again as it climbed out of the Sun's gravitational well. The perihelion velocity depends on the perihelion distance and the hyperbolic excess velocity. Closer perihelion means higher velocity at closest approach. For 0.39 astronomical units perihelion, the velocity would be about 70 kilometers per second. For 0.1 astronomical unit perihelion, roughly 200 kilometers per second. For 0.05 astronomical unit, about 300 kilometers per second. For 0.01 astronomical unit, approaching 700 kilometers per second. These velocities are extraordinary. 700 kilometers per second is roughly 0.2% of the speed of light. At such speeds, the comet would cross the Sun's diameter in less than 2,000 seconds, about half an hour. The high velocity means the comet spends very little time near perihelion. This is both good and bad for survival. Good because the exposure to extreme conditions is brief. Bad because the brief exposure occurs at maximum intensity. The orbital geometry also matters. The trajectory's inclination and orientation determine whether the comet approaches from the ecliptic plane or at steep angles, whether it passes in front of the Sun from Earth's perspective or behind it, whether the tail points toward or away from Earth. For maximum observability from Earth, you'd want the comet to pass the Sun at an angle that keeps it visible from Earth before and after perihelion, and ideally with the tail pointing in a direction visible from Earth. But the actual geometry would be determined by how the comet entered the solar system, which would be random. There's no reason to expect favourable observing geometry. The comet might pass behind the Sun from Earth's view, making observations impossible. The orbital velocity also creates a strong orientation effect. The comet's nucleus might tend to align with the velocity direction, due to aerodynamic-like forces from the solar wind and the asymmetric sublimation pattern. If elongated, the nucleus might point its long axis in the velocity direction, like an arrow flying through space. This would affect how tidal forces acted on it and how it fragmented. The orbital angular momentum, the rotational motion around the Sun, would be conserved unless the comet experienced significant non-gravitational forces. This conservation links the comet's velocity and distance, determining the trajectory shape. Non-gravitational accelerations from sublimation could slightly modify the orbit. If the sublimation was asymmetric, producing more thrust in one direction than another, the comet's trajectory would be deflected. For a close approach, non-gravitational effects might be substantial. The intense sublimation could produce accelerations of many meters per second squared, comparable to weak rocket engines. These accelerations could change the perihelion distance by thousands or tens of thousands of kilometers over the course of the approach. Whether this would make the approach closer or less close depends on the direction of the thrust, which depends on the sublimation asymmetry. Predicting the exact trajectory would be challenging. Observations far from the Sun would establish the initial orbit, but as the comet approached and sublimation intensified, its path might deviate from predictions. Orbital determinations would need frequent updating as new observations revealed trajectory adjustments. The final perihelion distance and time might differ from early predictions by significant amounts. After perihelion, if anything survived, the outbound trajectory would depend on the mass lost during approach. A comet that lost substantial mass would have slightly different orbital energy afterward, because the mass loss could occur asymmetrically, imparting momentum. But for a hyperbolic orbit with large excess energy, these effects would be small corrections. The comet would still escape the solar system, just on a slightly different path than it would have if it had been a non-sublimating object. The orbital period, the time for a complete orbit, is infinite for a hyperbolic trajectory. The comet would never return. It would make a single pass through the inner solar system and then depart forever. Its encounter with our Sun a unique event in its interstellar journey. The orbital mechanics thus set the stage for the physical processes. They determine when and where the comet experiences extreme conditions, how long it has to survive them, and what paths the fragments and debris follow after perihelion. Understanding the orbit allows predicting when and where to observe, what the encounter timeline will be, and how the resulting debris will be distributed through space. It's the kinematic framework within which all the thermal, tidal and chemical processes play out. As 3I/Atlas approached the Sun, its composition would change dramatically, transforming from a cold mixture of ices and dust into something very different through sublimation, chemical reactions, and selective loss of volatile materials. The initial composition would be characteristic of an interstellar comet, water ice as the main component, with carbon dioxide, carbon monoxide, methane, ammonia, and other frozen volatiles mixed in, plus silicate dust and organic compounds. This composition reflects formation in the cold outer regions of another star's planetary system, where temperatures were low enough for these volatile substances to condense as ices. As the comet warmed approaching the Sun, the volatiles would sublimate in order of their vapor pressures. The most volatile species would be lost first, at largest distances from the Sun. Carbon monoxide and methane would start sublimating beyond 10 astronomical units, where temperatures rise above roughly 30 to 40 Kelvin. These ices can't survive closer to the Sun than the outer solar system. Carbon dioxide would sublimate next, becoming active around 5 to 7 astronomical units as temperatures exceed roughly 70 Kelvin. Water ice would become active around 2 to 3 astronomical units as temperatures rise above about 150 Kelvin. By the time 3I/Atlas reached 1 astronomical unit, the surface layers would have lost most of their carbon monoxide, methane, and carbon dioxide. Water ice would be the dominant remaining volatile. Deeper in the interior, more volatile ices might persist if thermal conduction was slow enough. The comet could be compositionally stratified, with volatile depleted outer layers and relatively pristine interior. But during very close approach, even the interior would heat up, as surface material sublimated away, exposing deeper layers. Those layers would heat and begin sublimating. The compositional stratification would be eroded as the comet lost mass from the outside in. Chemical reactions could also alter composition. The intense ultraviolet radiation near the Sun can break molecular bonds and drive chemistry that wouldn't occur in the cold outer solar system. Water molecules could be photodissociated into hydrogen and oxygen. Further reactions might produce hydroxyl radicals, hydrogen peroxide, and other reactive species. Carbon dioxide and carbon monoxide could be broken down into carbon and oxygen atoms. These reactions would mostly occur in the coma rather than in the solid nucleus. But some radiation might penetrate the surface layers, driving chemistry in the outer micrometers or millimeters of the nucleus. The organic compounds in the comet would be particularly affected. Organic chemistry is sensitive to radiation and heat. Complex organic molecules might break down into simpler components or react to form new compounds. Some organics might polymerize, linking together into larger molecules. Others might decompose into simple hydrocarbons or be completely destroyed, leaving only carbon atoms. The dust composition would also evolve. Dust particles are typically mixtures of silicate minerals, organics, and sometimes metals. As the comet heated, the organic coatings on dust grains would vaporize, leaving bare silicate and metal grains. Very close to the Sun, the silicates themselves might partially vaporize or melt, transforming crystalline minerals into amorphous glassy materials or even into gas. The isotopic composition would change selectively. Light isotopes tend to be more volatile than heavy ones. So hydrogen would escape preferentially over deuterium, carbon-12 over carbon-13, oxygen-16 over oxygen-18. This isotopic fractionation would make the remaining material progressively enriched in heavy isotopes, as the lighter ones were selectively lost. The effect would be small but potentially measurable spectroscopically. The elemental composition would change as well. Hydrogen, helium, carbon, nitrogen, and oxygen, the most abundant elements in the original composition, would be lost as gas. Heavier elements like silicon, magnesium, iron, and sulfur would remain primarily in the dust. By perihelion, the material remaining would be enriched in refractory elements. If all the ice had sublimated, what was left would be essentially a rubble pile of dust and rock, very different compositionally from the original ice-rich comet. The gas released during approach would also evolve compositionally with time. Early in the approach, the gas would contain carbon monoxide and carbon dioxide from sublimating volatiles. Closer to the Sun, it would be primarily water vapour. Very close, it might include silicon monoxide and other species from vaporizing rock. Spectroscopic observations tracking this compositional evolution would provide information about the comet's internal structure and the sublimation sequence of different ices. Comparing early spectra with late spectra would reveal how composition changed with solar distance. The ultimate fate of the different compositional components would vary. Gases would disperse into space, either falling into the Sun, being blown away by radiation pressure and solar wind, or escaping on hyperbolic trajectories. Dust would follow size-dependent paths. Large grains would stay near the comet's orbit. Small grains would be pushed away by radiation pressure. The smallest grains would escape the solar system. The compositional legacy of 3I/Atlas after a close approach would thus be a dispersed cloud of material, chemically and isotopically transformed from its original state, spread through the inner solar system and beyond. Some atoms would be incorporated into the Sun, others would become part of the zodiacal dust cloud that fills the inner solar system. Others would escape to interstellar space, carrying a processed version of the comet's original composition back to the galaxy. Understanding these compositional changes helps us appreciate that the comet's destruction isn't just physical disintegration, but chemical transformation, a changing of state from organized molecular compounds to dispersed atoms, from structured materials to diffuse gas and dust. The Sun's magnetic field and the fields carried by the solar wind would interact with 3I/Atlas in complex ways during close approach. affecting how the ionized gas from the comet behaved and potentially providing observable signatures of the interaction. The Sun's magnetic field at the surface is structured and complex, with field strengths ranging from about 1 Gauss in quiet regions to thousands of Gauss in active regions and sunspots. This field extends out into space, weakening with distance but remaining dynamically important throughout the inner solar system. The field is carried outward by the solar wind, the plasma flowing from the Sun's corona. The magnetic field frozen into the solar wind plasma creates the interplanetary magnetic field, or IMF. This field has a characteristic spiral pattern called the Parker spiral, because the combination of radial solar wind flow and the Sun's rotation creates a spiral field structure. Near the Sun, within a few solar radii, the field is more radial. Farther out, it becomes increasingly spiral. 3I/Atlas passing through the inner regions would encounter magnetic field lines oriented in complex geometries depending on its exact location relative to solar structures. The comet itself initially has no significant magnetic field. The nucleus is not magnetic, and the neutral gas in the coma doesn't generate fields. But as gas becomes ionized by solar radiation, it becomes electrically conductive plasma that can interact with magnetic fields. The ionized gas in the comet's coma and tail would be affected by the IMF. Charged particles, ions and electrons, spiral around magnetic field lines and are constrained to move along them. This creates a magnetic confinement effect. The cometary ions can't move freely across field lines. They're funneled along the field, creating elongated structures aligned with the local field direction. The interaction also creates what's called a magnetized obstacle. The dense cometary plasma doesn't let the solar wind pass through it directly. Instead, the solar wind is deflected around the coma, carrying the magnetic field with it. This deflection creates a boundary structure. On one side is the solar wind and IMF. On the other is the cometary plasma. The boundary between them, called the contact surface, is a region of compressed magnetic field and plasma. In front of the coma, as the solar wind encounters the obstacle, a bow shock can form. This is a standing wave in the plasma where the supersonic solar wind slows down to subsonic speeds as it hits the cometary gas. The bow shock, if it forms, would be visible as a curved structure in front of the comet. Observations might show enhanced brightness or emission from the shocked plasma. Behind the coma, the deflected solar wind creates a tail structure. The magnetic field lines draped around the coma are pulled downstream, creating a tail that's both plasma and magnetically structured. This magnetic tail structure can show complexity. Field lines can be stretched, compressed, and can reconnect. Reconnection events, where oppositely directed field lines break and reform in different configurations, can release energy and accelerate particles. These reconnection events might create bright spots or moving features in the ion tail. They can also cause tail disconnection events, where part of the tail breaks off and drifts away while a new tail forms. Such disconnection events have been observed in comets encountering solar wind disturbances. They create visually dramatic changes in tail structure over hours. For 3I/Atlas very close to the Sun, the magnetic interaction would be particularly intense because the solar wind is denser and faster close to the Sun, and the comet would be releasing tremendous amounts of ionizable gas. The magnetic field strength near the Sun is also higher. At a few solar radii, field strengths could be tens to hundreds of Gauss in the regions between active areas and much higher in active regions. If the comet passed through a coronal streamer, a large-scale magnetic structure extending from the Sun's surface, the interaction could be spectacular. The comet plasma would be channeled along the streamer's magnetic fields, potentially creating narrow jets or filaments. Solar activity could dramatically affect the interaction. A solar flare occurring near the comet would subject it to enhanced radiation and particle fluxes. A coronal mass ejection could engulf the comet in a blast of magnetized plasma. If a CME struck the comet, the sudden pressure might compress the coma or even strip material from the nucleus through the enhanced drag forces. The magnetic fields in the CME might create bright emission features as they interacted with cometary ions. The magnetic interactions could be studied through several observable signatures. The ion tail structure reflects the magnetic field configuration. Spectroscopy can identify ionized species and their excitation states, which depend on magnetic field strength. Spacecraft with magnetometers in the inner solar system might even detect the localized magnetic disturbance created by the comet's presence, though this would require being relatively close to the comet. Radio emission might be generated by magnetic processes. Reconnection events, shock waves, and particle acceleration in magnetic structures can all produce radio waves at various frequencies. These radio emissions would be faint and difficult to detect, but could provide unique diagnostics of the plasma conditions and magnetic field strength that other observations can't easily measure. The magnetic interactions would also affect how comet material was dispersed. Ions confined to magnetic field lines would be transported along those lines, potentially over vast distances before recombining and becoming neutral atoms. This magnetic transport could carry material from 3I/Atlas far from its orbital path, distributing it through regions of space the comet never physically visited. The complex dance between cometary plasma and solar magnetic field would thus be an important component of the close approach physics, shaping the comet's appearance and behaviour in ways that pure gravitational and thermal physics wouldn't predict. Understanding these magnetic interactions requires sophisticated magnetohydrodynamic modelling, simulating plasma and magnetic field evolution simultaneously. Such models have been developed for comets at normal distances, but would need extension to the extreme conditions near the Sun. Understanding what would happen to 3I/ATLAS requires accounting for all the energy inputs and outputs, the full energy budget of a comet experiencing extreme solar conditions. Energy enters the system primarily through absorption of solar radiation. At any distance from the Sun, we can calculate the solar flux, the energy per unit area per unit time striking the comet's surface. This absorbed energy must go somewhere. It can heat the surface, conduct into the interior, drive sublimation, be radiated away as thermal emission, or power other processes like chemical reactions. The balance between these energy sinks determines the comet's temperature, sublimation rate, and evolution. Let's examine each component of the energy budget. Solar radiation absorption depends on the comet's cross-sectional area and albedo. A 3-kilometre sphere has a cross-section of about 7 square kilometres. With typical albedo of 0.04, it absorbs 96% of the light hitting it. At 0.1 AU, the solar flux is about 136,000 watts per square metre. The total absorbed power would be roughly 10 to the 12th power watts. 1 trillion watts. That's about the power output of a large power plant, all hitting a few kilometre object. It's an enormous energy input. Where does this energy go? The largest sink at close distances is typically sublimation. When ice sublimes, it absorbs latent heat. For water ice, about 3 million joules per kilogram. With 10 to the 12 watts of power and 3 million joules per kilogram of ice, you could sublimate about 300,000 kilograms per second. Over an hour, that's about 1 billion kilograms. Over the brief passage within 0.1 astronomical unit, tens of billions of kilograms. A 3-kilometre comet with density of 600 kilograms per cubic metre has total mass of about 10 trillion kilograms. Losing tens of billions is a fraction of a percent seemingly survivable. If gas escapes at 1 kilometre per second, which is typical for water vapour at a few hundred Kelvin, the kinetic energy is about 500,000 joules per kilogram. This is small compared to the sublimation latent heat, so the energy cost of giving gas kinetic energy is a minor term in the budget. Chemical reactions might consume or release energy. Endothermic reactions would cool the surface, while exothermic reactions would heat it. But for cometary materials, these effects are probably small compared to sublimation and radiation. The gravitational potential energy is another consideration. Material falling toward the Sun releases gravitational energy. For a comet at 0.1 astronomical unit, the gravitational potential is much lower than at 1 astronomical unit, meaning material has released energy falling inward. But this energy was released gradually over the entire infall and manifests as kinetic energy of the comet's orbital motion. It doesn't directly heat the nucleus. However, material ejected from the nucleus carries gravitational energy. Gas and dust blown away have to climb out of the Sun's gravitational well. This energy comes ultimately from the sublimation process, slightly reducing how much mass can be sublimated for a given energy input. For very close approaches, tidal energy becomes relevant. Tidal flexing from varying gravitational field strength as the comet rotates, or as it passes perihelion, could heat the interior through friction. This is similar to tidal heating in moons like Io orbiting Jupiter. But for a comet's brief passage near the Sun, tidal heating is probably minor compared to direct radiative heating. Putting all the energy terms together, we can construct a quantitative model of the comet's thermal evolution. The model would be a set of differential equations describing how temperature changes with time and position within the nucleus. Solving these equations numerically, we could predict temperature distributions, sublimation rates, and mass loss for different approach scenarios. Such models have been developed for comets at typical solar distances. Extending them to very close approaches requires handling more extreme conditions and potentially different physics, as temperatures reach regimes where new processes become important. The model results would tell us how quickly the comet loses mass, how deep the heat penetrates, how the nucleus temperature changes during approach and after perihelion. These predictions could be tested against observations of other sungrazing comets, refining the models to better match reality. For 3I/Atlas specifically, the energy budget analysis would reveal whether survival is plausible or impossible for a given perihelion distance, providing quantitative estimates to replace qualitative speculation. The energy perspective also highlights the extreme nature of close solar approach. The power levels involved, trillions of watts hitting a small object, are extraordinary. The comet is being hit by focused star power, a tiny glimpse of the tremendous energy the Sun produces continuously. Against such energy input, the structural integrity of ice and rock seems fragile. It's remarkable that anything can survive close solar approach at all. That some comets do survive shows the complex interplay between heating, sublimation cooling, structural properties, and the brief timescale of the passage. The energy budget thus provides the quantitative foundation for understanding the comet's fate, translating qualitative descriptions of heating and sublimation into numbers that can be compared with observations and used to make testable predictions. After 3I/ATLAS passed perihelion in a hypothetical close approach, what would remain would be a debris field. A cloud of fragments and particles following related but distinct orbits through the inner solar system. The debris field would result from the fragmentation and sublimation processes discussed earlier. Each fragment or particle ejected from the nucleus would become its own object following its own trajectory. The larger fragments, if any survived, would be on nearly hyperbolic orbits similar to the original nucleus's orbit. But small differences in ejection velocity would create different specific orbits. A fragment ejected prograde in the direction of orbital motion would have slightly higher orbital energy and a different orbital period. A fragment ejected retrograde would have lower energy. Fragments ejected radially toward or away from the Sun would have different perihelion distances. Medium-sized particles, tens to hundreds of microns, would experience intermediate effects. Radiation pressure would deflect their orbits but not completely dominate. They would follow curved paths, somewhat different from purely gravitational trajectories. The size distribution of the debris would determine its overall appearance and behaviour. If there were a few large fragments and many small particles, the field would be dominated by discrete bright spots from the fragments with a diffuse background from the dust. If the nucleus completely disintegrated into only small particles, the field would be entirely diffuse, a gradually expanding cloud with no discrete objects visible. The mass distribution among fragments matters greatly. Most of the mass might be in a few large pieces, with the particle cloud containing only a small fraction. Or the mass might be distributed among countless small pieces, none individually significant. Observations of other fragmenting comets suggest hierarchical mass distributions. The largest fragment contains perhaps half the total mass, the next few fragments contain progressively less, and the vast number of small pieces together contain a modest fraction. For 3I/Atlas, if it fragmented during close approach, we might expect one or a few fragments containing most of the mass, plus a cloud of smaller debris. The debris field would continue evolving after perihelion. Sublimation would continue as long as the fragments remained warm and had ice to lose. The smaller fragments would sublimate completely first, disappearing from view. Collisions between fragments are unlikely due to the huge volume of space and the dispersion of fragments. But it's not impossible. If two fragments happen to have very similar orbits and one caught up to the other, they might collide. A collision would produce more debris, shattering the fragments into smaller pieces. This would accelerate the disintegration process. The debris field would also interact with any solar wind structures it passed through. Streams of fast solar wind or the edges of coronal mass ejections might push on the ionized gas from the fragments, slightly deflecting the smaller pieces. Tracking the debris field would be challenging. The fragments would be faint and fast-moving. Many might not be detectable with current telescopes. We might observe only the largest few fragments and the general glow of the dust cloud. Spectroscopy of the debris would reveal composition changes. Different fragments might show different spectra if they came from different parts of the original nucleus with different compositions. The dust cloud would evolve chemically as solar radiation continued to process it. Organic compounds would be broken down, ices would sublimate from particles, grains would be heated and altered. Over months and years, the debris field would disperse throughout the inner solar system. The fragments would separate so much that the field would no longer be a coherent entity, but just individual objects on unrelated orbits. Some debris might eventually encounter planets. A dust particle or small fragment on a crossing orbit with Earth might enter our atmosphere as a meteor. Such meteors from 3I/ATLAS would be travelling very fast, at least 34 kilometers per second from the hyperbolic excess velocity, likely producing bright fireballs. They would be recognizable by their unusual trajectory, entering the atmosphere at angles or directions different from typical meteoroids from solar system sources. This information would be valuable for understanding cometary structure and how comets respond to extreme stress. Applicable not just to 3I/Atlas but to all comets that undergo close solar approaches. Throughout 3I/Atlas's close approach, spectroscopic observations would provide crucial information about physical conditions, composition, and processes occurring as the comet interacted with the extreme solar environment. For example, oxygen might be observed as neutral oxygen, singly ionized oxygen, or doubly ionized oxygen. The ratios between these species indicate the ionization equilibrium, which depends on radiation intensity and plasma density. Very close to the Sun, highly ionized species would appear. Silicon stripped of many electrons, iron in high ionization states, even elements like calcium and magnesium in unusual states not normally seen in comets. These exotic spectroscopic signatures would be smoking guns for the extreme conditions, impossible to produce except in very intense radiation fields. The spectral line widths would also provide information. Broader lines indicate faster atomic motions, either from high temperature or from bulk motion like expansion. Near perihelion, If material was being explosively ejected at high velocities, the emission lines would be Doppler broadened. The amount of broadening would tell us the ejection speeds, providing information about the forces driving the explosion. The continuum emission, the smooth background spectrum underlying the specific lines, would also evolve. Normally, cometary continua are dominated by sunlight scattered from dust, but near the sun, thermal emission from hot dust would contribute significantly. The continuum would show blackbody-like emission from dust at hundreds or thousands of degrees, appearing redder than reflected sunlight. If dust reached temperatures above roughly 1200 Kelvin, it would visibly glow, emitting most of its light in the near-infrared and red part of the spectrum. The comet would look reddish-orange from hot dust emission. Spectroscopy in the ultraviolet would be particularly informative. Many important lines from ions and highly excited atoms appear in the UV. Hydrogen, Lyman alpha, oxygen lines, carbon lines, all produce strong ultraviolet emission. Space-based UV spectroscopy from satellites or the Parker Solar Probe could observe these features if instruments were pointed at the comet during its passage. Infrared spectroscopy would reveal thermal emission from dust and potentially detect molecules that don't have strong visible or UV lines. Water, carbon dioxide, and organic molecules all have strong infrared spectral features. Magnetic effects might be detectable spectroscopically through Zeeman splitting. The small wavelength shifts that magnetic fields produce in spectral lines. Very strong magnetic fields near the Sun might create detectable splitting in some emission lines. Putting all the spectroscopic information together would provide a comprehensive picture of the physical and chemical processes occurring during the close approach. We could track the temperature evolution from continuum thermal emission and line ratios. We could measure ionization states and infer radiation field intensities. We could observe composition changes as different ices sublimated. The spectroscopic data would be limited by how well we could observe the comet during its passage. Some wavelengths might be observable only from space. Some might be impossible to observe due to solar glare. But the spectroscopic information we could gather would be among the most valuable data from the event, providing insights impossible to obtain any other way into the extreme physics and chemistry of a comet interacting with its star. To understand what might happen to 3I/Atlas in a close solar approach, we can look at observations of actual sungrazing comets that have passed very near the Sun, learning from their behaviour what to expect. The most famous sungrazing comets are the Kreutz family, believed to be fragments of a large comet that broke apart centuries ago. Members of this group are discovered regularly by the SOHO spacecraft's coronagraph. Over 2,000 Kreutz sungrazers have been catalogued since SOHO began operations in 1995. They approach the Sun with perihelia typically between 0.005 and 0.01 AU, just a few solar radii from the Sun's surface. Most Kreutz sungrazers don't survive perihelion. They're observed approaching the Sun in coronagraph images but don't appear on the other side. The interpretation is that they sublimate completely during close approach. The typical Kreutz comet is relatively small, perhaps tens to hundreds of meters across. At such sizes and at such close solar distances, the sublimation rates are sufficient to completely vaporize the nucleus in a matter of hours. But occasionally, larger Kreutz comets are observed to survive. These are bright enough to be seen not just in coronagraphs but also from the ground as they emerge from perihelion. A few comets have been observed to brighten dramatically near perihelion. One interpretation is that fresh ice is exposed by cracking or fragmentation, creating a burst of activity. The variability in behaviour suggests that cometary structure matters a lot. Comets with similar orbits can have very different outcomes depending on their size, density, composition, and structural strength. Second, size matters enormously. Small comets, hundreds of meters across, are unlikely to survive very close approaches. Large comets, several kilometers across, have better chances. 3I/Atlas at roughly 3 kilometers would be relatively large compared to typical sungrazers. This would improve survival prospects compared to smaller objects. Third, structural variations affect outcomes. We don't know how strong 3I/Atlas was internally. If it was a loose rubble pile like many comets, it might fragment easily. If it had more cohesion, it might hold together better. Fourth, composition matters. Comets with higher dust-to-ice ratios or more refractory materials might survive better than those that are mostly volatile ices. We don't know 3I/Atlas's composition in enough detail to predict this factor. The observations of actual sungrazers provide crucial reality checks on theoretical models. The models need to match what we actually see happen to real comets to be credible. When models predict that a comet should survive but observations show it doesn't, or vice versa, it indicates our understanding is incomplete. Refining models to match observations improves our ability to predict outcomes. The sungrazer observations also show that each comet is unique. Even within the same family with presumably similar origins, individual comets behave differently. Some survive, some don't. Some fragment, some stay intact. This variability reminds us that predicting exactly what would happen to 3I/Atlas is impossible without knowing details we don't have. We can estimate probabilities and likely outcomes, but certainty isn't achievable. The comparison also highlights the scientific value of sun-grazing comets. Each one provides data about cometary behavior under extreme conditions. Each observation refines our understanding. 3I/ATLAS, had it approached closer to the Sun, would have provided exceptional data as a large interstellar comet experiencing extreme conditions. The observations would have been scientifically priceless. But the actual sungrazers we can study provide a framework for imagining what might have been, showing us the range of possible behaviours and outcomes that comets experience when they venture too close to stellar fire. Despite the destructive nature of a very close solar approach, such an event would provide extraordinary scientific opportunities to study processes and conditions rarely accessible to observation. The study of cometary interiors would be one major opportunity. Normally, we can only observe a comet's surface. The interior composition and structure remain hidden beneath layers of ice and dust. But during extreme sublimation, the surface layers would be stripped away rapidly, exposing deeper material. We would effectively be drilling into the comet through natural processes, revealing its internal structure. Spectroscopic observations could detect molecules released from different depths, providing information about compositional stratification. If the comet formed with layered structure reflecting changing conditions in its origin protoplanetary disk, close approach might reveal those layers. The study of extreme sublimation physics would be another opportunity. Most cometary sublimation occurs at moderate solar distances where rates are relatively low. Close approach would push sublimation into regimes rarely studied. How does ice behave when it's receiving millions of watts per square meter of radiation? Does it sublimate smoothly or explosively? How do the sublimation products expand away from the nucleus? These questions could be addressed through observations of 3I/ATLAS during close approach. Providing data for refining models of ice physics under extreme conditions. The material strength and structural properties of cometary nuclei could be inferred from how the nucleus fragmented. The size distribution of fragments, the way they separated, the patterns of breakup all provide information about internal structure. If 3I/Atlas behaved the same as solar system sungrazers of similar size, that would suggest comet formation processes are universal. If it behaved differently, that might indicate compositional or structural differences from its exotic origin. The event would also test and improve our models across multiple disciplines. Thermal models, structural models, chemical models, plasma models, all would be confronted with data from an extreme test case. Models that successfully predicted the observations would be validated. Those that failed would need refinement, pushing our understanding forward. The public engagement opportunity would be significant as well. A bright sun-grazing comet visible even in daylight would capture public imagination. and provide a teachable moment about comets, solar physics, and planetary science. Educational materials developed around the event could reach millions of people, inspiring interest in science and astronomy. All these opportunities would need to be balanced against the challenges of observation and the brief timescale of the event, coordinating international observation campaigns, allocating spacecraft and telescope time, preparing instruments and analysis tools, would all require rapid organisation. But the scientific community has experience with such rapid response campaigns from previous comets and solar system events. The infrastructure exists to mobilise quickly when necessary. The opportunities would be fleeting. The most extreme phase near perihelion might last only hours, but those hours would provide data potentially informing decades of research across multiple fields. In this sense, 3. I/Atlas's hypothetical close approach would be a scientific bonanza, a rare chance to push our understanding into extreme regimes and test theories against nature's most demanding conditions. As we've explored the hypothetical scenario of 3 I/Atlas approaching very close to the Sun, it's worth reflecting on the relationship between this scenario and what actually happened. Between speculation and observation, the actual 3 I/Atlas passed perihelion at 0.39 astronomical units, experiencing significant heating and activity, but nothing like the extreme conditions we've been imagining. It survived its passage intact, or at least without obvious complete fragmentation. It developed a coma and tail, but remained a coherent object observable for months. The scientific data gathered from the actual passage was valuable, but reflected relatively normal cometary behaviour. The comet was unusual in other ways: its interstellar origin, possibly its composition, perhaps its structure, but its response to solar heating was within the range of typical comets. A hypothetical closer approach would have been a different story entirely. The physics we've discussed, extreme heating, tidal disruption, complete sublimation, represents what could have happened but didn't. This raises a philosophical question about counterfactual scenarios. What's the value of exploring what didn't happen? Why imagine scenarios that weren't realised? One answer is that understanding what could have happened helps us appreciate what did happen. By knowing that 3 I/Atlas could have been destroyed had its trajectory been slightly different, we better understand the factors that allowed its survival. The actual trajectory wasn't inevitable. It was the result of the comet's specific velocity and direction when it entered the solar system, which were determined by its history and the random gravitational influences it experienced during interstellar space. A different history, a slightly different velocity, and the trajectory would have been different. The fact that we can imagine alternative scenarios highlights that what we observed was one outcome among many possibilities. The thought experiment approach also helps identify key physics. By varying parameters in imagination, we can see what matters most. Is perihelion distance more important than approach velocity? Is size more critical than composition? Working through hypothetical scenarios builds intuition about how the physics works. What processes dominate in different regimes? How different factors interact? This intuition is valuable when we encounter new comets with different properties. Having thought through various scenarios, we're better prepared to predict what will happen and to interpret what we observe. The counterfactual exploration also serves narrative and educational purposes. The story of what could have happened to 3 I/Atlas is dramatic and engaging in ways that the actual observation might not be. The hypothetical close approach of 3 I/Atlas embodies this alternative reality thinking. It wasn't just fantasy, but a genuine possibility that physics allowed, that could have happened given slightly different circumstances. Perhaps in some parallel universe where 3 I/Atlas entered the solar system with a slightly different velocity, the close approach did occur. Astronomers in that universe observed the spectacular destruction we've imagined, but in our universe, the actual moderate passage is what happened. We can observe the reality while also understanding the alternatives. This dual perspective, appreciating both what was and what could have been, provides the richest understanding of the phenomena we study. Science isn't just about cataloguing what is, but about understanding the space of possibilities, the range of outcomes that natural laws allow, and the factors that determine which possibilities are realised. The hypothetical close approach of 3I/Atlas, while it didn't occur, still teaches us real physics and deepens our understanding of comets, the sun, and the processes that would unfold should such an encounter ever happen. Studying what would happen to 3I/Atlas in extreme close approach to the sun, even though it didn't actually occur, provides valuable lessons that extend beyond this specific scenario to broader understanding of physics and astronomy. By studying extremes, we gain insight into what processes are capable of when pushed to their limits. How fast can ice sublimate? How completely can materials be vaporized? What happens when tidal forces exceed structural strength? Understanding how these processes interact, which dominates how they affect each other, requires thinking about complex systems rather than isolated effects. This systems thinking is valuable across science. Most natural phenomena involve multiple processes. Understanding them requires synthesis, putting together knowledge from different domains. The extreme scenario also teaches about timescales near the sun. Processes that normally take days or weeks happen in minutes or hours. Sublimation accelerates, fragmentation occurs rapidly, chemical transformations proceed quickly. This temporal compression provides a different perspective than slower processes. It highlights what can happen when rates increase, revealing phenomena that might be invisible in slow processes but become dominant in fast ones. Understanding timescale effects helps us recognize that the same underlying physics can produce very different observed behavior depending on how fast things happened. The lesson about boundaries and transitions is also important. As 3I/Atlas approached the sun, it would transition from one regime to another, from cold to hot, from solid to gas, from coherent object to debris field. Understanding these transitions, where they occur and what drives them, provides insight into boundaries that appear elsewhere in nature. Phase transitions, threshold effects, tipping points, all involve similar physics of systems changing state. The irreversibility of extreme destruction is another lesson. Once 3I/Atlas sublimated completely, it couldn't reform. The transformation from organised structure to dispersed gas was one way. This irreversibility is fundamental to thermodynamics. Entropy increases, order tends toward disorder. Close solar approach would maximise entropy, transforming the structured comet into maximum entropy gas. But even in destruction, there's creation. The atoms dispersed from 3I/ATLAS would eventually be incorporated into other objects. Cosmic recycling means nothing is truly destroyed, just reorganized. The lesson about observational challenges in extreme environments is practical and important. Studying objects close to the sun is difficult. The techniques required differ from typical astronomy. Developing methods to observe in challenging environments, using coronagraphs, timing observations carefully, coordinating multiple platforms, these skills generalize to other difficult observational problems. The lesson about the value of imagination in science is perhaps most fundamental. Science isn't just passive observation of what is, but active exploration of what could be. Thought experiments, hypothetical scenarios, counterfactual reasoning, all are legitimate scientific tools when used carefully with attention to physical principles. Einstein famously used thought experiments to develop relativity. Imagining riding a beam of light or experiencing gravity in an accelerating elevator helped him see relationships that observation alone didn't reveal. Similarly, imagining 3I/Atlas. Approaching the sun reveals relationships between heating, sublimation, tidal forces and disruption that observation of its actual passage wouldn't show as clearly. The lessons from studying extremes thus extend far beyond the specific scenario. They provide general insights about physics, about scientific methodology, about how to think about natural phenomena. Whether or not any comet actually experiences the extreme close approach we've imagined, the exercise of thinking through what would happen develops understanding valuable for real astronomy and science. 3I/Atlas's hypothetical close solar approach connects to broader questions about how comets and small bodies interact with stars throughout the universe, processes occurring countless times across the cosmos. Our Sun is one of roughly 200 billion stars in the Milky Way galaxy. Most of those stars probably have planetary systems, based on exoplanet surveys showing planets are common. If planets are common, then the processes that form planets, including formation of comets in outer planetary regions, are probably common too. Comets likely exist around most stars. Such comets might experience repeated close approaches to different stars in the binary system, being gradually torn apart over multiple passages. Around massive stars that end their lives in supernovae, comets present during the explosion would experience radiation and particle fluxes billions of times more intense than anything near the Sun. These comets would be instantly vaporized, contributing negligibly to the supernova's energy, but experiencing the most extreme comet destruction imaginable. In the dense star clusters at galactic centers, comets might be perturbed by close stellar encounters more frequently than in the galactic disk. The comet populations might be depleted more quickly from repeated disruptions. Around the supermassive black holes at galaxy centers, tidal forces become strong at much larger distances than around stars. Comets approaching too close would be shredded by tidal effects at distances where stellar radiation would still be relatively weak. The cosmic context also includes the role of comets in delivering material between stars. Interstellar comets like 3I/ATLAS, ejected from one system and entering another, carry material across light years. If such a comet approached its new host star closely enough to fragment and sublimate, it would deposit material from its origin system into the new system. This represents a form of material exchange between stellar systems. Over billions of years and trillions of comet transfers, significant amounts of material might be exchanged between systems. This cosmic recycling homogenizes galactic composition to some degree. The formation of new stellar systems from molecular clouds that contain processed material from previous generations includes contributions from countless destroyed comets. When 3I/ATLAS formed around its distant parent star billions of years ago, the material it condensed from probably included atoms that had passed through previous comets and been processed by previous stars. This universality is a fundamental principle of physics. The same laws operate everywhere. Understanding processes in one context allows predicting them in others. The hypothetical close approach of 3I/Atlas serves as a case study of universal processes, a specific example illuminating general principles that operate throughout the universe wherever comets and stars interact. Our ability to even imagine what would happen to 3I/Atlas approaching the Sun closely reflects centuries of scientific progress in understanding comets, the Sun, and the physics governing their interactions. Ancient observers saw comets as mysterious harbingers, atmospheric phenomena or divine portents rather than astronomical objects. The idea that they were solid bodies orbiting the Sun wasn't established until Tycho Brahe's observations in the late 1500s. Edmund Halley in 1705 predicted the return of the comet now bearing his name, proving comets followed gravitational orbits. This was a major step in understanding comets as natural phenomena governed by physical law. Through the 18th and 19th centuries, observations accumulated showing comets had nuclei, comas, and tails. The material nature of these components was debated, with various theories proposed. The realization that sunlight and solar radiation pressure shaped comet tails came in the late 1800s. This connected cometary phenomena to solar physics, an important conceptual step. Fred Whipple's dirty snowball model in 1950 proposed that comet nuclei were mixtures of ice and dust. This model, confirmed by spacecraft observations decades later, remains the foundation of comet understanding. The space age brought direct observations. Spacecraft flying by comets revealed nuclear structure, measured composition directly, observed sublimation processes up close. Missions like Deep Impact, which deliberately crashed into Comet Tempel 1 in 2005, showed that nuclei were fragile and porous, fundamentally different from solid rocks. Numerical simulations could track how a comet nucleus would heat up, where cracks would form, when fragmentation would occur, in detail impossible with analytical mathematics alone. Observations of sungrazers by SOHO and other spacecraft provided empirical data about extreme comet-sun interactions. This data tested and refined models, showing what actually happens in the extreme environment. The discovery of interstellar objects beginning with 1I/Oumuamua in 2017 opened new questions about comets from other stellar systems and how they compared to solar system comets. 3I/Atlas's detection and study in 2024 represented the newest chapter in this evolving understanding, providing the first good spectroscopic and physical data on an interstellar comet. The hypothetical close approach scenario we've explored draws on all this accumulated knowledge. We can predict what would happen because we understand thermal physics, structural mechanics, plasma interactions, and orbital dynamics. Our ability to make detailed predictions that are probably broadly correct reflects how far scientific understanding has progressed. Medieval astronomers couldn't have imagined what we now know about comets and the Sun. But our understanding remains incomplete. There are still uncertainties about comet internal structure, about how exactly tidal disruption proceeds, about details of sublimation physics at very high rates. Every new observation provides opportunities to refine understanding. Comets continue to surprise us with behaviours our models don't quite predict, showing we still have more to learn. The evolution of understanding is ongoing. Future spacecraft missions, better telescopes, more sophisticated computer models, all will contribute to deeper knowledge. Eventually, we might have good enough understanding to predict with confidence exactly what would happen to any given comet in any given solar approach, accounting for all its properties and all environmental conditions. But we're not there yet. Our current understanding is good enough for reasonable predictions, but not for certainty. There's still room for surprises. This incompleteness is part of what makes science exciting. There's always more to discover, always opportunities to improve understanding, always new observations that challenge and refine theories. The hypothetical close approach of 3I/Atlas represents our current best understanding applied to an extreme scenario. Future scientists with better knowledge might predict different details. But the general picture, heating leading to sublimation, tidal forces causing fragmentation, material dispersing through the solar system, is probably robust. The basic physics is well enough understood that major surprises are unlikely. The evolution of understanding thus provides both confidence that our scenario is plausible and humility about the details. We know enough to imagine what would happen, but not everything about exactly how it would unfold. This is the nature of scientific knowledge. Progressive improvement toward more complete understanding. Always advancing, but never truly finished. Throughout our exploration of 3I/Atlas's hypothetical close approach, we've discussed largely destructive processes: sublimation, fragmentation, vaporization, dispersal. Yet there's a certain beauty in these processes when viewed from the right perspective. The aesthetic beauty is perhaps most obvious. A bright comet with a massive tail glowing in colours from multiple emission processes, set against the backdrop of the Sun, would be visually spectacular. Historical accounts of great comets describe them as among the most beautiful natural phenomena ever witnessed. A comet approaching very close to the Sun would potentially surpass any historical example in brightness and tail extent. The physical processes themselves have elegance. The equations governing thermal conduction, orbital mechanics, and gas dynamics are mathematically beautiful, symmetric and general. The energy flow is aesthetically satisfying. Solar energy, generated by fusion in the sun's core, radiates outward and is captured by ice, driving sublimation. The energy that took thousands of years to reach the sun's surface is absorbed in moments, transforming matter from solid to gas. This rapid energy transfer and transformation shows nature's efficiency in redistributing energy according to thermodynamic principles. The second law of thermodynamics, that entropy increases, plays out dramatically. The creation of new structures from destruction also carries beauty. As the comet fragments, each piece becomes a new object with its own identity and trajectory. The one becomes many. There's also beauty in our human ability to understand these processes. That minds that evolved to survive on one small planet can comprehend the physics of comets, and stars shows the power of human intelligence and curiosity. The scientific understanding is itself a thing of beauty, a structure of knowledge built collaboratively over generations, refined through observation and thought into coherent frameworks that explain and predict. The aesthetic appreciation of knowledge, of understanding how nature works, is as real as visual aesthetic appreciation. Comprehending why things happen as they do brings a satisfaction comparable to seeing beauty in art or music. The precision of prediction is beautiful too, that we can calculate from first principles what should happen to a comet approaching the sun and have those predictions match observation shows the universe operates according to comprehensible laws. This comprehensibility is not obvious or guaranteed. The universe could have been chaotic and random, resisting understanding. That it instead follows orderly principles we can discover is remarkable and beautiful. The connection between small and large scales has aesthetic appeal. The same physics governing a comet near the sun applies to stellar processes, galactic dynamics, cosmology. Universal principles unifying diverse phenomena show the deep simplicity underlying apparent complexity. Even the destructive power has a kind of terrible beauty. The sun's immense energy, capable of vaporizing rock and tearing apart a kilometers-wide object, displays nature's raw power operating according to inflexible physical law. There's something awe-inspiring about witnessing, even in imagination, processes operating at such intensity. It reminds us of the extremes nature encompasses, far beyond human daily experience. The transience of the phenomenon contributes to its beauty. The close approach would be brief, the most intense phase lasting perhaps hours. This fleeting nature makes it precious. A rare alignment of circumstances creating something unique. Beauty often involves uniqueness and transience. A sunset is beautiful partly because it's temporary, changing moment by moment, never exactly repeating. The comet's destruction would be similar, a one-time event, never to recur exactly. The narrative arc from approach through destruction to aftermath also has aesthetic structure. Beginning, middle, end. Tension building as the comet approaches, climax at perihelion, resolution as fragments disperse. Humans find well-structured narratives satisfying. The natural phenomena obligingly follow a narrative structure because physical processes have characteristic progressions determined by underlying causes. Ultimately, finding beauty in destructive processes reflects a mature scientific aesthetic that values understanding and process over preservation and stasis. Not all beauty lies in eternal unchanging forms. Some beauty is found in transformation, change. The working out of natural principles regardless of consequences to particular objects. The destruction of 3I/Atlas would be beautiful, because it would reveal physics operating at intensity, show matter, and energy transforming according to fundamental law, and remind us of the vast power and elegant simplicity of the natural world. As we conclude our exploration of what would happen if 3I/ATLAS approached too close to the sun, it's worth reflecting on the questions that remain, the uncertainties that persist even with current scientific understanding. The first enduring question is about the specifics of any individual comet's response to extreme conditions. Even with good models, predicting exact behaviour requires knowing properties we often don't measure well: internal structure, composition variations, mechanical strength, density distribution. For 3I/Atlas specifically, many properties remain uncertain despite the observation campaign in 2024. We have estimates of size and composition, but don't know internal structure or how homogeneous it was. The magnetic interactions near the Sun involve plasma physics in complex geometries with variable field strengths. Models exist but are simplified. The full three-dimensional time-dependent behaviour is difficult to simulate accurately. Observations of actual sungrazers provide some constraints, but can't measure everything we'd like to know about the magnetic environment and plasma conditions. The question of long-term dispersal of material from a destroyed comet remains open. Where exactly does the material end up? How much falls into the Sun versus escaping the solar system? How long does it take dust to disperse through interplanetary space? These questions require tracking many particles over long times through complex force environments. Simulations can approximate the outcomes, but with significant uncertainties. The comparison between interstellar comets and solar system comets is still based on very limited data. We've observed only a few interstellar objects. Are they representative of the broader population or outliers? If we observed 100 interstellar comets, we'd have better statistical understanding of their properties. With 3 examples, 1I/Oumuamua, 2I/Borisov, and 3I/Atlas, we can only tentatively generalize. The question of how common close solar approaches are for interstellar comets depends on understanding the distribution of trajectories for objects entering the solar system from interstellar space. That distribution depends on the local distribution of stars, their motions, how many comets they eject, and other factors involving galactic dynamics. Constraints exist, but uncertainties remain large. Whether we'll detect another interstellar object passing very close to the Sun depends on survey capabilities and luck. With better telescopes and more sensitive surveys, detection probability increases, but close approaches might still be rare events. The ultimate question of how much we could learn from such an event if it occurred remains partly unknowable until it happens. Real observations always reveal unexpected details that no model predicted. Each comet provides surprises. Even normal comets often behave in ways that require extending or modifying models. An extreme event would likely provide even more surprises. These enduring questions don't diminish the value of current understanding. We know enough to make reasonable predictions and to recognize what we don't know. Acknowledging uncertainty is part of honest science. The questions motivate continued research. Each observation of sungrazers, each improvement in modelling techniques, each laboratory experiment on cometary materials contributes to reducing uncertainties. Progress is incremental. We may never have perfect prediction of individual comet behaviour, but we can continue improving statistical understanding and refining models to better match observations. The enduring questions also make the subject alive and interesting. If everything were fully understood with no mysteries remaining, there'd be little motivation for further study. The fact that questions persist, that we can imagine scenarios we can't fully predict, that each observation has potential to surprise, keeps the field vital and engaging. For 3I/ATLAS specifically, the questions about what would have happened in a closer approach will likely never be definitively answered. The event didn't occur, and we can only estimate what would have happened based on physics and comparison with other comets. But the exercise of thinking through the scenario, working out what physics predicts, identifying where uncertainties lie, has value regardless of whether we get to test predictions against reality. It develops understanding, builds intuition, identifies important questions for future research. These are the true goals of science. not just cataloguing what happened, but understanding principles that explain why things happen as they do. The enduring questions thus don't represent failure, but opportunity, chances to learn more, refine understanding, push the boundaries of knowledge further into the unknown. Thank you for journeying with me through this long exploration of a scenario that didn't happen but easily could have. We've spent these hours contemplating what would unfold if 3I/Atlas had taken a different path, approaching too close to the Sun and experiencing the ultimate test of stellar fire versus cometary ice. I hope you found peace in this exploration, discovered calm in following physical processes to their inevitable conclusions. Sometimes there's comfort in understanding how nature works, even when understanding reveals destruction rather than preservation. Wherever you are now, I hope you're ready for deep rest. Your breathing has found its gentle rhythm. Your mind has released its grip on details and conclusions. The processes we've explored perhaps help put daily concerns in perspective against the cosmic scale of stars and comets. Sleep well tonight, knowing that the universe operates according to comprehensible principles. Comets and stars interact in ways we can predict and understand. The physics is beautiful even when the outcomes are destructive. Dream peacefully of visitors from distant stars, of trajectories shaped by gravity and chance, of ice meeting fire in the space between worlds. Dream of atoms cycling through different forms across cosmic time, never created or destroyed but endlessly transformed. Good night. May your sleep be undisturbed and restorative. May tomorrow find you refreshed. And may you carry forward an appreciation for the physics that shapes our cosmos, the processes that operate whether we observe them or not, according to laws that are universal and eternal. The scenario we explored didn't happen to 3I/ATLAS, but somewhere in the galaxy, it's probably happening now to some other comet approaching some other star. The physics we've discussed is real and universal, even if our specific example was hypothetical. Good night.